Okay, now that we have a little bit of familiarity with this three-dimensional coordinate system, R3, let's take a look at the concept of distance inside that coordinate system. And we'll start off with a very simple example, as we are wont to do. We want to find the distance, let's suppose from the origin, of course we're talking about ordered triples now, 0, 0, 0, to, how about that point we looked at earlier, 2, comma, 3, comma, 5. Picture is helpful, as it often will be in this class, if we can draw pictures in R3. And of course, if you just practice it a little bit, you will get much better at it as you go along. So again, we went from 0, 0, 0 to the point 2, 3, 5. So we sort of sketch this out like so. So here's our point 2, 3, 5. Looking for the distance, that means we're looking for basically the diagonal of this parallelepiped. So we want to find the distance, the length of that line segment right there, which we'll call D. Well, how can we do that? Well, good old Pythagoras should help us out here. First of all, let's find this, which I'll call R. How could you find the length of this segment right here? That's just in the xy plane, this little R segment here. So R is equal to, well, let's see, I guess our x value here and our y value here. Our x distance plus our y distance, I guess r squared is equal to that, right? So r is equal to the square root of that. And in this case, that's the square root of, how far do we travel on the x-axis? 2 units. And the y-axis, 3 units. So 2 squared plus 3 squared. And so r squared, let me go back to r squared, is just 2 squared plus 3 squared, or x squared plus y squared. Well, again, Pythagoras tells us that if we take this right triangle right here, this is our z-axis, which is equal to 5, and so that value d, that line segment d, is the hypotenuse of this right triangle, with one leg being r and the other leg being z. So d squared is equal to r squared plus z squared. R squared is equal to x squared plus y squared. And so d itself is going to be the square root of x squared plus y squared plus z squared. That's if we're coming from the origin. We just take the coordinates, square them, add them, and take the square root. So we get the square root of 2 squared plus 3 squared plus 5 squared. Oh, it's 4, 9 is 13. 13 and 25, I guess, is 38. The square root of 38 is our distance. So, of course, we want to generalize that for any 2 points. We want to be able to find the distance between any 2 points. And we'll call those points x1, y1, z1, and x2, y2, and z2. And of course, what we're going to do then is we're going to take our x value of the first point and the x value of the second point and find the distance. So the distance is going to be, well, the distance squared will be the difference of our x value squared plus the difference of our y value squared plus the difference of our z values squared. Of course, you can't subtract in either order since you're squaring. It's the distance itself, very familiar, hopefully. It looks just like the distance formula in R2, only with another variable added. And that'll be the case for a lot of the stuff we come across. It'll look just like what we did in R2 in 2 dimensions, only we'll just add one more variable here. And so if we think about that, if we have a concept of distance, then we can talk about certain equations of things. Remember the idea of a circle in R2. We'll say with a center at HK and a radius of R. Well, the definition of the circle was all the points that are a distance of R away from HK. So we want all xy whose distance from HK, which is this formula, is equal to R. Squaring both sides, we get our standard equation for a circle, which is this right here. Well, what's the analogous shape in R3? If we take a circle, add a dimension, what do we have? That's right, we have a sphere. So we have a sphere in R3, and let's suppose it has a center of, oh, how about H, K, and L, and a radius of R. So we want all points x, y, and z that have a distance, a fixed distance of R from HKL. So we want r to be the distance from x, y, z to HKL, and so we use our distance formula here. We have r would be equal to the square root of x minus h squared plus y minus k squared plus z minus l squared. Squaring both sides, we have our standard equation for a sphere in R3, x minus h squared plus y minus k squared plus z minus l squared is equal to our radius squared. Let's take a look at an example here of this in action. Let's suppose we want to find the equation of the sphere with, we'll say, a center of 2, -2, +6, and radius 4. Well, it's very simple. This is our h, our k, and our l. This is our r, and so we want x minus 2, that quantity squared, plus y minus a minus 2, that quantity squared, plus z minus 6 to be equal to r squared, 4 squared. And so making this look a little bit nicer, we would have x minus 2 squared plus y plus 2 squared plus z minus 6 squared equals 16. And there it is in standard form. And of course, if I gave you this equation right here, you need to be able to recognize that, hey, that's the equation of a sphere in R3. The center is 2, -2, 6, and the radius is the square root of 16, which is 4. Now, things aren't always going to be presented quite so nicely. For example, suppose I want you to find the center and the radius of the sphere given by the following equation: x squared plus y squared plus z squared minus 2x plus 8y plus 10z plus 5 is equal to 0. We're going to use a process here called completing the square. We would say it this way: we're going to complete the square in the variables x, y, and z. We know it's going to be a sphere because x, y, and z are all squared and they all have the same coefficient. In this case, it's 1. So I'm going to rewrite this, grouping my variables together. So x squared minus 2x leaves some space. Y squared plus 8y leaves some space, and z squared plus 10z leaves some space. I'm going to go ahead and throw this 5 on the other side, equals -5. Now, remember how to complete the square. What we do is we cut the coefficient on the linear term in half, square it, and add it. So I'm going to add, well, 2 divided by 2 is 1. 1 squared is 1. You can take -2 divided, because you're squaring it, so it's going to be positive either way. 8 divided by 2 is 4. 4 squared is 16. And 10 divided by 2 is 5. 5 squared is 25. Now remember, I have to add those things to the right side of my equation as well. So I have to add 1, 16, and 25. We've got to keep everything balanced. Now, completing the square the way we've done it should allow us to factor. Not only will this equation factor on the left side, but these three trinomials, we'll have a plus here and a plus here, should factor into two of the same thing, and that's going to be the case. This factors into x minus 1 quantity squared. This factors into y plus 4 quantity squared. And the last trinomial on the left side factors into z plus 5 quantity squared. On the right side, well, let's see, that's -4 plus 16 is +12 plus 25, I guess 37. Didn't turn out to be too nice, but that's okay. Our center then is going to be the values that make these quantities 0. That's 1, -4, -5. Our radius is the square root of the right side, which is 37. Okay, a couple other things that we want to be able to do in this introduction to three-dimensional space. One of those is to be able to sketch solids, or at least be able to recognize what a solid would look like. A lot of times it's easier to sort of see it in your mind and a little bit more difficult to put it down on paper. Let's suppose I told you this inequality right here, and I wanted you to sketch that inequality in R3. So you want all ordered triples where the y value is 0 or bigger, 4 or less. X, y, and z can be anything you want them to be. So here is our three-dimensional coordinate system, x, y, and z. We just care about the y values going from 0 to 4. So we're going to have a plane on the left, this y equals 0 plane on the left. That's just the xz plane. Okay, there's y equals 0. And then we're going to have this y equals 4 plane on the right. So let me see if I can sketch that. Again, just for this simple thing, it already gets a little bit on the messy side, y equals 4 right there. But then, of course, we're going to have everything in between those two planes. So we're going to be on or in between those two planes, and of course they extend up infinitely far in the positive z, positive x, negative x directions. So I hope you get the idea. That's not my best three-dimensional picture there, but I hope you understand. We have that plane cutting through the y-axis at 4, parallel to the xz plane. And then we have the xz plane itself. Those are the boundaries, and then every point in between those is included as well. Let's try one or two more of these. Let's say I want to sketch this inequality. Okay. I want x squared plus y squared plus z squared to be greater than or equal to 4, and at the same time less than or equal to 16. Hey, no problem, right? Well, let's think about what we have here. Remember that x squared plus y squared plus z squared equals 4. That is a sphere, center at the origin. Radius is what? Hope you said 2 and not 4. Remember, it's the square root of 4. If you said 2, that's good. So we have that, and then the other equality here is x squared plus y squared plus z squared equals 16. That's also a sphere. Same center. Different radius. Bigger radius, the square root of 16, which is 4. So we're going to need to mark off to 4 on our axes here, x, y, and z. And what we're going to have basically is all the points on or outside this smaller sphere, but on or inside this bigger sphere. So here's our smaller sphere of radius 2. It comes like this. Okay, so we're going to be on that, but inside of this bigger sphere of radius 4 here. And so it's again hard to see, but it's going to be well, kind of everything in between those two spheres. So you have basically a ball with the core removed is how you can think of that, and that's the solid that we're talking about here. The solid region in between the sphere of radius 2 and the sphere of radius 4. And with that, my friends, I think we are in good shape to tackle that first homework assignment, 9.1. And to do that, of course, you are going to need your password. And here it is. Again, by putting this in, you are saying you have watched this video, you've read that section of the book, you are ready to attempt this homework. The password is defalcation, and I'm sure you probably know already what that means. Well, the act or instance of embezzling. So if you're stealing money in a systematic way, you're engaging in defalcation. It can also mean just a failure to meet a promise or an expectation. That's probably a little more less common of a usage, but defalcation, the act or instance of embezzling. I really have no way to use this in a sentence that would relate at all to what we've talked about today, but type that in, get cracking on 9.1, and if you get stuck, please let me know if you have any questions.